Back with the Chapter 3 AP review outline. This is where we talked about linear regression. And we talked about an explanatory variable, which that's used to explain the observed outcomes. And the response variable measures the outcome of the study or the experiment. So the explanatory variable is the X, the response variable is the Y, independent, dependent. If you're asked to describe a scatter plot, we use the acronym DOFS: direction, outliers, form, strength. Direction could be positive or negative. Excuse me. Strength could be weak, moderate, or strong. You'll notice I put in LY. Like I encourage you to use LY here, words here like moderately strong, moderately weak. And it just depends on the correlation and the amount of scatter between the points. The form is either going to be linear or curved. You could have clusters, very unlikely that you just have like two clusters, but I wanted to put that in there. Correlation, we only use if we have a linear model. And it tells us three things: the direction, the strength, and the form. The closer to 1 or -1, the stronger the relationship. If you need to use the calculator to find a least squares regression line, plug your explanatory variable into list 1, your response variable into list 2, and then I've kind of walked through how to do that. You do need to make sure your diagnostics are on. That's done by hitting second 0. Might as well do it right now. Second 0. You're in alpha mode, so go down to letter D, diagnostic on. Make sure you turn that on. Because if you don't, you're not going to see the correlation or R squared when you do a regression. Once you get the regression, you're just substituting in the context. Remember that symbol means predicted number of cars. If R is close to 1, does that mean getting older causes us to own more cars? Absolutely not. Correlation does not prove causation. Association does not prove causation. One of the huge takeaways from this class. If we switch the explanatory and the response, the amount of scatter between the points doesn't change, so the correlation stays the same. If we switch the explanatory and the response, the least squares regression line will completely change because now we're predicting the age and not the number of cars. If we talk about interpreting R squared and S, R squared is literally just the correlation squared. We call it the coefficient of determination. It's the percent of the variation in the response variable that's explained by the least squares regression line. So here, 98.1% of the variability in the number of cars can be accounted for by the least squares regression line. S is the standard deviation of the residuals. So the interpretation when using the least squares regression line to make predictions, we'd expect to be off by about 2.1 cars on average between the actual and the predicted. Our predictions are going to be off by about 2.12 cars on average. One other thing that I'll mention, they could ask you to interpret the slope and the y-intercept. So if we start with the y-intercept, if we have a brand new, if somebody is 0 years old, if they're a newborn, we would predict that they've owned negative 21.82 cars. Typically, you're not going to be asked to interpret the y-intercept because it doesn't make sense, as in this example. For the slope, for each additional year in age, the predicted number of cars owned increases by 0.9. So for each additional year in age, the predicted number of cars owned increases by 0.9. Okay. Is this point influential? Influential points have a big impact on the slope of the y-intercept. So if we ran the regression with and without this point, or looked at the least squares regression line with and without, the answer here is yes, because the slope and the y-intercept change dramatically when this point's removed. And in order to tell, influential points are typically outliers in the x direction or the horizontal direction and cause the line to be pulled towards them. The other thing that we covered was actually in section 12.2, what we included in this chapter. It was dealing with re-expression. If you don't have linear data and you need to re-express by doing log or natural log or square root or something like that. And then you have to be able to back solve. So if you have a re-expression with a log, you're going to end up needing to do 10 to some power or hitting second log on the calculator. And if you have natural log, you're going to need to do e to some power or second natural log on the calculator. Simple example, if you have the natural log of some variable you're predicting equals 4, it's e to the 4th equals that predicted value. And that's going to show up on the calculator. If I do second natural log, it automatically puts e raised to, and then I can figure that out. That's the quick review for chapter 3.